In this video, I want to do another 3x3 example, so the second of 3 examples. So in this example, what we're going to do is we're going to study the matrix A being 4, 3, 1, 5, 2, 5, 0, 0, 2. And again, I want to find the eigenvalues and eigenspaces. So I want to find the eigenvalues and eigenvectors, or eigenspaces. Eigenspaces are the vectors that, eigenvectors are the vectors that span the eigenspaces. So these are really two interdependent ideas. So let's just go through and do the computation. We want to compute the determinant of A minus lambda I. So that's going to be the determinant of, we're going to take A, and I'm going to subtract lambda from the diagonal terms, and the rest stays put. So 3, 1, 5, 2, 5, 0, 0. And let's see, when we take the determinant, let's just make life as easy as possible on us. Let's look at expanding along the last row. So this is going to be 2 minus lambda times the determinant of the corresponding submatrix. So it's going to be 4 minus lambda, 4 minus lambda times 2 minus lambda minus 15. And so that's 2 minus lambda times 8 minus 6 lambda plus lambda squared minus 15. And that works out to be 2 minus lambda times lambda squared minus 6 lambda minus 7. So that's our characteristic polynomial. And I guess we should add that this is 2 minus lambda times lambda minus 7 times lambda plus 1. So really that's our characteristic polynomial. These are all the characteristic polynomial, but that's the easiest one to work with. So our eigenvalues are going to be the solutions for lambda when our p of lambda is 0. And that's going to be when lambda is 2, 7, or negative 1. All of these eigenvalues have multiplicity 1, so that part works out nicely. That means that the eigenspaces are all going to have dimension 1. And so let's see here. So for our eigenvalues, let's just go through and let's think about what happens for each of the different eigenvalues. Say lambda equals 2. If lambda is 2, what we're going to do is, remember, we're going to solve a minus 2i times x equals 0. And that works out to be, let's see, if lambda is 2, we're going to end up with 2, 3, 1, 5, 0, 5, 0, 0, 0. 5, 0, 5, 0, 0, 0. And so let's think about what's going to happen there. So if lambda is equal to 2, what we're going to end up with, if we do some row operations here, is you could certainly do 1, 0, 1, 2, 3, 1, 0, 0, 0. And even more than that, let's see, we could take negative row 1 and add it to row 2, or even negative 2 row 1 and add it to row 2. And so that would give us, let's see, if we take negative 2 row 1, add it to row 2, we would end up with 0, 3, negative 1. Okay, and so what we end up with is, let's let x3 be t. x2 then is going to be 1/3 t, because remember that this means that x1 plus x3 are t, 3x2 plus negative x3 are 0. x1 plus x3 is 0. So x3 is t, and if x3 is t, then 3x2 is going to be t, so x2 is 1/3 t, x1 is negative t. And so our eigenspace, E2, is going to be the set of vectors of the form negative t, comma, 1/3 t, comma t, where t is any real number. And that's the span of the vector negative 1, 1/3, 1. And if I want, I can multiply that vector negative 1, 1/3, 1 by negative 3. And those two vectors will have the same span. So this would be, if I multiply by negative 3, we would get that this would be positive 3, negative 1, negative 3. Okay. So we've got 3, negative 1, negative 3. That's E2. And then let's do the same for the other eigenvalues. So we had lambda equals 7. Here, if lambda is equal to 7, then a minus lambda I is going to be equal to 0. We've done this enough. Let me just jump right to solving the augmented matrix. A minus 7i goes on the left here, so if lambda is 7, this will be negative 3, 3, 1, 5, negative 5, 5, and 0, 0, negative 5. And it turns out that if you simplify this, you can see that this will turn out to be 1, negative 1, 0, 0, 0, 1, 0, 0, 0. Just mentally so that you know what I was doing there, you can take this first quantity, make it a 1, and then that cancels the rest. And then these other two quantities are the same, so you can divide the top by 3 and the bottom by negative 5, and you end up with the same thing. And those are really just multiples of 1, negative 1. So anyways, so that's how quickly you can solve this. It turns out that this is going to lead us to x3 is 0, x2 will parameterize by t, and x1 will be negative t. Nope, x1 will be positive t. They'll be the same. Because I know that x1 minus x2 is 0. So if x2 is t, then x1 has to be the same t. And therefore, e sub 7 is going to be the span of the vector 1, 1, 0. Okay, because it's really, you can think of this as going to be the vector t, t, 0, where t runs through R, right? And so that leads you to 1, 1, 0. Anyways, so that's the eigenspace e sub 7. Again, one-dimensional because it's the span of a single vector. Finally, if we have lambda is negative, what was our other eigenvalue? Lambda is negative 1. Then we're going to look at a minus lambda I being 0. That's going to lead us to study this augmented matrix. A plus I is going to be, let's see, 5, 3, 1, 5, 3, 5, and 0, 0, 3. And this is going to be almost identical to what we did before, except this is going to be 5, 3, 0, 0, 0, 1, 0, 0, 0. So the steps are basically the same in the mental arithmetic there. So 0, 0, 0. This is supposed to be a dotted line here. Okay. And if we want to parameterize this, again, we get the x3 is 0. If I call x2 t, then x3 is going to be negative 3/5 t, because I know that 5x1 plus 3x2 is 0. So x1 will be negative 3/5 x2. And so I could write that e minus 1, so the eigenspace corresponding to the eigenvalue minus 1 is going to be the span of the vector, and this x3, by the way, should be an x1. I apologize. So x1 is negative 3/5 t. So e negative 1, this eigenspace, is going to be the span of the vector negative 3/5, 1, 0. Or we can scale this and get the same span. So if I multiply everything by -5, this will end up being the span of the vector 3, -5, 0.